I'd like to introduce our final speaker for today. He is the Director of R&D at Anritsu Company, where he oversees the development of various test and measurement instruments. He's well recognized in the field of frequency synthesis and is referred to as the inventor of quick syn technology. Now, in 2009, he received the ARMS, that's spelled ARMMS, RF and Microwave Society's Best Contribution Award for his work on fast-switching frequency synthesizers. He has written more than 50 technical articles and holds 6 US patents. He is senior IEEE member. Ladies and gentlemen, let's welcome Dr. Alexander Chenakin.
Thank you. Ladies and gentlemen, good afternoon. My name is Alexander Chenakin. I am the Director of R&D at Anritsu Company. The Anritsu Company is located in California, in the United States, and we develop and manufacture various test and measurement equipment such as vector network analyzers, signal generators, spectrum analyzers, and power meters for various applications, including communication such as 5G, and we do a lot of research also looking for potential 6G solutions. And the subject of my today's presentation is frequency synthesis in new rubidium technology that brings high stability and exceptional spectral purity. Oops. Okay. So first of all, frequency synthesizers. Why do we need them? The frequency synthesizer is a key component of virtually any RF, microwave, test and measurement, communication, and monitoring systems. It's normally used as a local oscillator, on the transmitter side in the up conversion schemes, as well on the receiver side on the down conversion schemes. What is the frequency synthesizer? Well, the frequency synthesizer can be treated as a black box that translates one or more signals called reference into a number of output frequencies within the desired frequency range with the desired step size. Well, normally, ideally, we would expect a very clean signal, which ideally should be represented as a very thin line in the spectrum domain. But in reality, any method creates some artifacts called spurs. In addition, the synthesizer frequency normally is not quite stable, but can move around, and this effect is called frequency instability. Furthermore, it can move faster, so our eye and available equipment cannot catch it statically anymore, and it appears as noise fluctuations called phase noise. Well, long story short, the job of any frequency synthesizer designer is to minimize all these effects, such as spurs and phase noise. Okay, why phase noise is so important? Having good phase noise is so important. You can see here phase noise of two hypothetical frequency synthesizer. The first one has very good phase noise, which is represented by this black line. and we see a signal we need to identify, we need to resolve. We can see that is above the phase noise curve, so we can identify this signal. But if we use a different synthesizer with worse phase noise, represented by this gray line, then this signal, desired signal, will be masked under phase noise, and we will not be able to resolve that. So if excessive phase noise limits the ability of the system to resolve a signal of small amplitude. That's why phase noise is very important and can and should be minimized, should be brought to small values, as small as possible. This year we introduced, just very recently introduced, a new signal generator. The core product is branded under Rubidium name, which has very unique features and performance, which essentially redefine the industry standards for spectral purity and stability. We have two models, two Rubidium signal generators covering 9 kilohertz to 20 and 43.5 gigahertz with very good step size, very small step size, an exceptional spectral purity, atomic grade stability, and in-field frequency and power calibration capabilities. In general, frequency synthesizer designers use various methods to synthesize a signal, such as direct analog synthesis, direct digital synthesis, and indirect or PLL synthesis. In our Rubidium signal generators, we use an innovative direct-indirect technique, which essentially combines and represents the best aspect of each methods. How does it work? How do we achieve good phase noise? This slide represents a simplified, I would say a very simplified block diagram of the Rubidium frequency synthesizer core. A key component here is a broadband YIG oscillator, which covers 2 to 20 gigahertz frequency range with very low phase noise, such as minus 170 dBc per hertz at high frequency offsets. Now we need to lock this YIG oscillator using a PLL loop. And normally, traditionally, people use frequency dividers inside the loop. And phase noise, all phase internal residual phase noise sources are degraded by 20 log n, where n is the division factor of such a divider. In our design, we use no frequency divider at all. Rather, we use a direct analog converter, which is a chain of mixers. As a result, we have no phase noise degradation because there is no divider. But that's not all. Furthermore, we insert a frequency multiplier inside the loop. And frequency multiplier works exactly opposite compared to a hypothetical frequency divider, meaning that instead of phase noise degradation, it rather brings phase noise improvements using the same 20 log n rule. Essentially, we create noiseless parallel loop, which has very minimal or no phase noise degradation, and that allows us to achieve very, very low phase noise. But how low? How much? What is the limitation? Is there any limitation? Of course, we still need to obey the laws of our mother nature, or laws of physics, if you will. In this case, our limitation is the phase noise of available reference. And in order to minimize that phase noise, we use a very complex reference by combining 4 different sources, such as 10 megahertz OCXO, which is overnight crystal oscillator, 100 megahertz OCXO, and 1.6 gigahertz DRO, dielectric resonator oscillators, which are locked to each other. And this chain is furthermore locked to a rubidium oscillator. What can this give us? Well, it allows us to provide the lowest phase noise at any given frequency offset. For example, in this slide, we can see how we construct the phase noise profile. This region, this blue region between 10 Hertz and 200 Hertz, the phase noise here mainly depends on the 10 megahertz OCXO. The green box around 1 kilohertz mainly depends on 100 megahertz OCXO. This region is provided by 1.6 gigahertz DRO, which has better phase noise in this specific region. And above that, we can see phase noise of the YIG oscillator. So the combination of this different reference source allows us to squeeze every drop of phase noise and provide the lowest possible phase noise profile at any given frequency offset. To be specific, we achieve minus 140 dBc per hertz phase noise at 10 gigahertz output and 10 kilohertz offset, which is better, well, actually way better compared to traditional techniques and instrumentation currently available on the market. You can see here real measurement data. The yellow curve is, well, it represents phase noise at 10 gigahertz, and this is 10 kilohertz offset point. You can see the marker. We are achieving better than minus 140 dBc per hertz, very low phase noise. If we go down in frequency, phase noise further improves at 6 dB per octave rate. For example, at 5 gigahertz, the phase noise is 6 dB better, and at 2.5 gigahertz, it's 6 dB even better. Very low phase noise. Interestingly, this method works equally well for spurious suppression too. Here's a typical spurious performance, and you can see that typically we achieve spurs better than minus 100 dBc, which is a fantastic value, keeping in mind that we work in very wide frequency range. We can see some, I would say, anomalies here and there, but the numbers are still very low, below minus 90 dBc. And interesting, Interesting question if it belongs to the signal of a rubidium signal generator or the test equipment we use, which is never perfect at all. So overall, we have very low spurs in the order of -100 dBc or below -100 dBc, very low. Also, we have very good harmonic suppression due to using very sophisticated switch filter banks. The second harmonic is below -60 dBc, and the third harmonic and higher harmonics are even lower, including subharmonics, which are better than -80 dBc. So harmonic wise, we also have a very clean signal. Well, in many applications, people need high output power, and we do provide high output power option. This is a power plot between 2 and 20 gigahertz. We can see we are above 30 dBm, so we can easily provide 1 watt, still keeping good phase noise and low spurs. The next aspect related to this technology is frequency stability, which mainly depends on the available time base. And historically, time base went from mechanical pendulum to mechanical clock and now to crystal oscillators, which are supposed very stable devices, and that's why they are normally used in traditional test equipment. But I can say that any crystal oscillator, its frequency, resonating frequency, depends on its dimensions, the resonator dimensions. And if temperature change, the dimensions of the resonator slightly change, and we will see some frequency instability. Furthermore, with time, the crystal material simply evaporates. The resonator becomes smaller and frequency change. So this effect is called aging. So although crystal oscillator is generally very stable, but there are still some secondary effects which require time to time to recalibrate the output frequency. In our case, we make one more step further, very radical step. Instead of relying on crystal oscillators, we utilize atomic rubidium source, and the frequency generated by atomic source does not depend on dimensions anymore, but it rather depends on physical constants, specifically on the energy level between different atom states and Planck's constant. Once again, doesn't depend on dimensions anymore, but rather on fundamental physical constants. That's why we achieve radically better frequency accuracy and stability. So as an option, we implement atomic standard inside this signal generator, which offers superior frequency stability compared to conventional overnight crystal oscillators. Furthermore, we have a built-in GPS receiver. Well, not just GPS, we also support Galileo, Baidu, GLONASS, all GNSS standards. That means we can receive a signal from cesium clock from satellites. And just with a push of button, we can recalibrate the frequency at customer location, not sending the unit back to the factory for recalibrating. Similarly, the rubidium signal generators provide a capability to calibrate output power as well. As an option, we provide a power sensor which can be plugged into a USB slot and connected to the synthesizer output directly, or to a DUT to remove some loss and frequency characteristics of cables, etc., etc. And once again, with just a push of button, we can recalibrate the output power without sending the unit back to the factory. And it's very important in many specific, very sensitive applications when you cannot just send the unit back to the factory often for recalibration. You can do it right at your facility, which is again very important in some applications, and also simply convenient for the end user, and it simplifies the recalibration process. To summarize the features of this new technology and the new signal generator, I can say that the rubidium signal generator provides exceptional spectral purity. Specifically, it provides minus 140 dBc per hertz phase noise at 10 gigahertz output and 10 kilohertz offset, which is supposed to be the industry. Currently, it's the industry lowest phase noise for broadband RF microwave signal generator instruments. Another feature is atomic grade stability, and as I mentioned, the rubidium signal generators offer superior frequency stability compared to conventional signal generators based on conventional crystal oscillators such as overnice crystal oscillators. And finally, it provides in-field calibration capability to adjust its internal time base as well as output power, which is important in many applications. Of course, it has many other features and options such as modulations, different modulation formats such as amplitude, frequency, phase, pulse modulations, and their combinations like chirp modulations to simulate different standards and different to support many different modulation schemes. We introduced this instrument very recently, and it generated a lot of interest within the industry. And recently, Microwave Journal has recognized this product as the most valuable product by Microwave Journal. Well, for the sake of time, I would like to conclude here. to leave some time for questions. I would like to thank you for your attention. And if you have any questions, I will be happy to answer.
Hi, Dr. Alexander Chenakin. Thank you so much for that wonderful presentation. And of course, with that, we'll now be moving on to the Q&A. And we've got several questions from the audience right over here. Starting with this one. And it's this. You said that rubidium signal generators offer the industry lowest phase noise. Can you be more specific? I mean, for example, how is rubidium phase noise compared to current modern high performance signal generator in the market?
Well, as I said, it provides the lowest phase noise as of today. If we compare with some very popular devices, for example, Keysight, PSG, and we consider their lowest ultra-low phase noise option, our rubidium signal generator provides more than 10 dB better phase noise, which is a big move, big advance in the signal generator technology.
Thank you so much. Move on to our second question in the lineup, and it's this. Can you calibrate rubidium output power not at the output connector but at a DUT plane? Can that be done?
Yes, absolutely. As I said, we provide power sensor. You connect it directly to the synthesizer output and calibrated at the output of the synthesizer. But if you have your device under test DUT and some cables in between or other device which have frequency variations, you can connect the sensor right at the DUT plane, press a button, and the power will be calibrated and will have very stable, predictable power right at the DUT plane, which is very helpful in some applications.
And another question that we have here is, how do you analyze rubidium signal generator spurs to ensure that they belong to the signal generator itself, but not to a spectrum analyzer? How can we do that?
Sorry, belongs to this, you mean the spurs?
That's right.
Yes,
how do you analyze?
It's a good question, because any signal generator generates spurs, no doubt. It's just there is no ideal device. We live in not ideal world. And the spurs level is so low, it's very difficult to detect and identify if it belongs to the signal generator itself, or for example, a spectrum analyzer we use to test and measure spurs. What do we normally do? We use two different spectrum analyzers, absolutely different, from different companies, let's say. And we rely on the fact that they're built using different architecture, and consequently, they have their own spurs at different places. So we connect first the spectrum analyzer A, measure spurs, and identify some bad points. Now, the next question is, do they belong to the signal generator or to the spectrum analyzer? We memorize these points and rerun the test with another spectrum analyzer B, just at these points. If these spurs disappear, then the conclusion is they did belong to the spectrum analyzer 1, but not to the signal generator. This is very helpful technique which allows us to identify false spurs, um, analyze spurs, and provide correct data.
Thank you so much. Now we still have a couple more questions over here that we hope to go through. The next question is, what is the highest operating frequency of the rubidium? Do you have any plans to extend its frequency range?
Yes. As of today, we released two models working up to 20 gigahertz and 43.5 gigahertz. Again, so as of today, the highest operating frequency is 43.5 gigahertz. We are also developing and planning to release soon a 70 gigahertz version. And we do recognize then, in order to extend the frequency bandwidth, which is very important for 5G and more incoming 6G applications, we need even higher frequencies. So we do plan to go to higher frequency to 110 gigahertz and even higher. We don't know yet where 6G will be operated at this frequency, but we know they will be higher than existing ones. So we do recognize this and expect to extend frequency range step by step.
Yes, and of course, we've got another question from the audience, and this person says, "Good presentation, doctor. Please, does this mean the machine can be easily to calibrate it by using GNSS antenna? What is the accuracy?"
Correct. In order to calibrate the frequency and get the right frequency, we need to compare it to a standard. And the primary frequency standard for frequency is cesium clock. And for GNS system, we know that they are operated using cesium clocks which are circling the Earth. So we have a GNS receiver which receives this signal, and using this signal we can calibrate the frequency very accurately, as accurate as the primary cesium standard is. And it can be done again very easily, just using an antenna and pushing a button without sending the units to the factory for recalibrating, which is very convenient in many applications.
Thank you so much for that explanation. And we have another question here, and this question says, "Why do you use a dielectric resonator oscillator, or DRO? Does it perform better than an oven-controlled crystal oscillator or an OCXO?" Would you be able to explain this one?
Yes, that's the thing. Crystal oscillators or overnight crystal oscillators, OCXO, normally have very low phase noise. But at certain frequency offsets, for example, above 10 kilohertz offset, a DRO, dielectric resonator, provides a better phase noise if I normalize or recalculate it to the same frequency. So it does have advantage over crystal oscillators in the 10 kilohertz to few hundred kilohertz offsets region. And once again, using different oscillators, different technologies, we optimize and minimize phase noise at any given frequency offset.
Thank you so much, Dr. Alexander Chenakin, for that deep discussion that we just had on a new rubidium technology brings high stability and exceptional spectral purity. Thank you so much for answering all those questions as well from our audience. Thank you so much, Doctor.
Thank you, everybody, for the opportunity to share some of our research and recent results. Thank you for your attention, and I really appreciate that. Thank you very much.